Hello everyone, welcome to my YouTube channel. So in this video, we're going to be looking at how to solve a differential equation with Python. Okay, and we are going to be making use of sympy library. Okay, so we'll be solving just one differential equation, and I think we should go for example 3. This one right here. Okay, so let's get started. I have my Jupyter Notebook environment open already. So the first thing I'm going to do is to import the sympy library. But if you don't have sympy, you can install it from within the notebook environment. Then pip install sympy. Then you run this. You run it by clicking on this button right here. But I already have sympy, so I don't need to install it again. All I have to do now is to say from sympy import, spell that wrong, import everything. Okay, so asterisk here means I'm trying to import everything in the sympy library. Okay, so we run this and it looks good. Okay, so we are solving for y of t according to this differential equation, but solve for y of t. So t is our independent variable and y is our dependent variable. So I'm going to define a symbol for the independent variable t. And we define symbol using the symbols function, and you put the character you want to represent as a symbol. Right? So I'm defining t as a symbol, and I'm going to be storing it in a variable t. Okay, I hope that makes sense. So this is my independent variable. Now, how do I define the dependent variable, which is y of t? Y of t is a function of t, right? So I have to use the function method, or the function method. And I'm defining y as my function, and y itself is a function of t, right? So I can store this in a variable called y as well. So this y here is a symbol, which is a function of t, and t itself is a symbol, okay? So I can run this, see there is no problem. So next thing we need to do is to define what our derivatives are. Because since this is a second order differential equation, it has the dependent variable y, its first derivative, which is y prime, and its second derivative, which is y prime prime. So we have defined y already, which is what we have here in the third cell. Now I need to define my first derivative and second derivative of y with respect to t. So how do I do that? I can create a variable named dy dt, and dy dt is actually the derivative of y with respect to t. So the way you define that in sympy is to write y dot diff with respect to t. So everything here represents y prime right here. Okay? So this is y prime, and I have stored it in a variable dy dt. Similarly, I can define my second order derivative as d square y dt squared and that's equal to y dot diff t2. So 2 here means that this is a second derivative with respect to t. So everything here is the same thing as d square y dt square, or y prime prime. You could also define it using double t here. It's basically the same thing. It means you're differentiating, you are getting the derivative of the second derivative of y with respect to t. Okay, so run that. Now we have the components of our differential equation. Now we need to form the differential equation itself. So you notice all equations, right? They have left-hand sides and right-hand sides. So for the problem we are solving, our left-hand side is everything here, and our right-hand side is everything here. So the way you define equations in sympy is to use the EQ function, and you write what you have on the left-hand side first, followed by what you have on the right-hand side, and both are going to be separated by a comma, as we'll see right now. So our equation is y prime prime minus 6y prime plus 15y. So I know y prime prime is everything here, right? So you can type d square y dt squared minus 6 multiplied by y prime. And y prime is the y dt plus 15 multiplied by y. Okay, now if you look at all these variables, these are the variables we defined in lines 3, 4, and 5. We have just multiplied them with some kind of constants, 6 for the y dt and 15 for y. D square y dt square has no coefficient. So that's my left-hand side. So to write the right-hand side, just have to separate by a comma. And I believe we have 2 sine 3t. So that's going to be 2 multiplied by sine, open brackets, 3 multiplied by t. Now I have access to the sine function because I imported everything within the sympy library into this working environment, right? If I did not import everything using asterisks, then I would not have access to the sine function. And of course, Python would not know what I'm talking about. Okay, so that's where the sine came from. Likewise, the diff function, this function itself, and symbols, okay? Everything came from within the sympy library. Okay, so let's run this, and we can see that this gives us our differential equation, right? It's just written in a reversed manner, giving us y of t first, that's 15 multiplied by y of t, minus 6 multiplied by dy dt, right? Plus d square y of t over dt squared. So basically, we've been able to write this differential equation in sympy. So we can store this in a variable called diff eq. See, if I run this again, we get nothing, but I can print out what I have in that variable by just writing the variable name. And you see we have our differential equation. So all of this equation is contained within our variable. So now we want to solve the differential equation. How do we solve the differential equation? To solve the differential equation, we use the function dsolve, and we pass in our differential equation into it. If I run it, we see that we have the solution to our differential equation. So we were given, of course, this is not the complete solution because we do not have the coefficients. These are just two coefficients, C1 and C2, as you would expect to get from a second order linear differential equation. So how do we solve for C1 and C2? We already know the structure of our results, which is everything we have here. So this is our y of t, and that's the solution to the differential equation. So to solve for, okay, we could store this in a variable and call that results. So if I try to print out results, see it's just the solution to our differential equation. So now I could actually break down this result into left-hand side and right-hand side, right? So I could just say result.RHS. So let's start with LHS first, and that's y of t. So it gives me just what is on the left-hand side of the equation. And similarly, results.RHS gives what you have on the right-hand side of the equation. Okay, so the variable result holds the whole equation with me, like I said earlier with differential equation if eq. Okay, so what we really need to work with is our right-hand side. The right-hand side of the differential equation. So we are going to be substituting values for the initial conditions, right? We're given the initial condition y of 0 to be equal to -1 and y prime of 0 to be equal to -4. So that means somehow, some way, I have to find, I have to substitute t to be 0 into this equation and equate that to -1. That's for the first initial condition. For the second initial condition, I have to differentiate the results, substitute 0 for t, and equate that to -4. So that's what we'll try to achieve right now. Okay, so I could define a variable called equation 1. Equation 1 for substituting t to be 0 and obtaining the result of -1. So I'm going to define that as EQ, then results, RHS. Now you use the subs method. We apply the subs method on results.RHS to substitute values, right? So in the subs method, you pass in a dictionary as an argument, and the key to the dictionary is the variable you are trying to substitute for, which is t in this case. And the value for the key is going to be the actual value we are substituting into the equation, right? So we are substituting 0. 0 is our value, and t is the key. So as you remember, when we are using EQ, we have left-hand side and right-hand side, right? So the left-hand side is everything I have here, which is just the whole of this equation with t as 0. Then on the right-hand side, we have -1. So if I run that, doesn't print out anything, but let's see what we now have in equation 1. Okay, so we have C2 plus 1 divided by 10 equal to minus 1 rather. So we could reassign equation 1 because we want to simplify this, right? So sympy can help us simplify this using the simplify function. So we just want to simplify equation 1. So this is equation 1, everything here, and we want to simplify it and reassign it to equation 1. So that means we are trying to change the value of equation 1 to a better form. So let's run it and let's see what we have. So you see now that equation 1 has been simplified and we have a value for C2, which is minus 11 divided by 10. All right. So now we need to substitute values for the second initial condition. But first, we need to differentiate the right-hand side of our result to get y prime. Then we substitute t, we substitute for t, and we equate that to minus 4. So to differentiate the function, we use diff. I believe we've seen that somewhere. Okay. We use diff to differentiate, but you don't dot it with anything, just like we did here. You just pass in the function you want to differentiate into the diff function. Okay, so let's see what that looks like. Let's differentiate. Remember what we're trying to differentiate is everything here. So we just have to pass in results.RHS. It's an error. Oh, sorry, we need to specify the variable we are differentiating with respect to. So I'm differentiating with respect to t. Don't forget, this is what we are trying to differentiate, which is everything here. And we're trying to differentiate it with respect to t, hence the second argument here. So if I run this, you see it gives us the derivative of the whole function. So we could save that in a variable called results diff. If I run this, it's nothing, but still get to see results diff. All right. So now this is the derivative of our result, right? The derivative of everything here on line 13. So now equation 2. Equation 2 is what we have when we substitute for t into this equation, into the result diff. So this is going to be results underscore diff subs, passing our dictionary T0. That's for the left-hand side. Remember, we're using the EQ method. And we pass in, so that's minus 4. Okay. So we pass in minus 4. Let's run that. No error. So what do we have in equation 2? All right, so we have square root of 6c1 plus 3c2 plus 1 divided by 10 equals to minus 4. All right, so equation 2 is easy to solve because we have a value for C2 already. Okay, so what we can do is, okay, we assign equation 2 to the equation 2 we just got, which is everything here dot subs. Now we're trying to substitute for C2. Since we have C2 already, we're trying to substitute for C2 in this equation. So how do we do that? We pass in our dictionary, then type C2. And what's the value for C2? The value for C2 is simply equation 1, which is what we have right here. Remember, equation 1 is C2 equals to minus 11 divided by 10. So we're trying to pass in equation 1 dot right-hand side because what we actually need is what is on the right-hand side of the equation, which is minus 11 divided by 10. Okay, so let's run this. It gives no error. Now what does equation 2 look like now? Okay, so you can see that right now we have substituted for C2, and now we have just C1 and a bunch of values. So we could easily simplify equation 2 and we assign it simplify equation 2. So let's run that. Gives no error. So what's equation 2 now? Okay, so now we have a value for C1 and C2. Okay, so let me just display equation 1 above it. All right, so we have our differential equation. We have a value for C1 and we have a value for C2. Now what we need to do is to substitute these constants C1 and C2 into the actual results that we obtained. Okay, that's into results.RHS. So let's do that. And you can store that in a variable called final results. Final results is just results that's right hand side dot substitute. We pass in our dictionary. Value for C1 is just equation 2. That's right hand side. That's what we have here. 2 root 6 divided by 15. Negative of that. Then a value for our C2. So C2 has a value of equation 1, equation 1 dot right hand side. Okay, so let's run that. No error. And let's print out our final results. Okay, so this is what the final results of the differential equation looks like. Now let's check out the solution on the website and see. This was actually solved using Laplace transform. Okay, but we should have the same results. Okay. All right, so it's just a slightly different way of writing the same results. Because I believe some terms are similar. Cos 3t divided by 10, sin 3t divided by 30, then minus 11 over 10. So yeah, they look similar. Minus 11 over 10, sin 3t divided by 30, cos 3t divided by 10. Yeah, so I believe they are the same, exact same equation. So guys, this is okay. Before we end the video, let's just try to see a plot of our results. So we can plot any equation in sympy using the plot function. So let's plot this final results. And I can pass in a range. Let's say -2, between -2 and 2. Let's run that and wait for sympy to plot that expression. So meanwhile, guys, okay, so yeah, this is what the results looks like on graph. So guys, I hope you have gained a lot from this video. To learn more about sympy, you could easily just go through their documentation. And you see, we have a whole bunch of explanations here, including how to install Anaconda. Okay, when you install Anaconda, you have access to Jupyter Notebook, which I used throughout in this video. So you can install that, can go through some tutorials, like calculus. Let's see that. Okay, so you can see how symbols were defined, how everything was imported, just like we did, and how to differentiate. See, this is just a way of differentiating cos x with respect to x, and of course, you know that is sin x. So, you know, the documentation is quite detailed. So, and of course, Python is very easy to follow. So, if you have any questions, please drop them in the comment section, and I'll also put a link to this webpage in the description, and a link to a repository on GitHub where you can have access to this notebook. Okay, so feel free to ask any questions, or if there are any other videos you'd like to see, please put them in the comment section, and I'll try as much as possible to make videos on them. And of course, don't forget to like the video and subscribe to my channel for more content, as that would only encourage me to do more. So thank you very much for watching, and I'll see you next time. Bye-bye.